Okay, in this lecture, we're going to discuss the arithmetic and logic instructions of 80, 8086, 8088 Intel's processors. Okay, these instructions, unlike the move instruction, these instructions will affect the flags. So the flag bits are going to be affected in using arithmetic or logic instructions. And by flag bits, we mean the carry flag, the sign flag, the zero flag, the parity flag, and the overflow flag. Okay, the first instruction we're going to discuss is the addition instruction. There are three forms of the addition. You add two numbers, you add including the carry, add with carry two numbers, or you increment a number by one. And here are the mnemonic codes of these three instructions. For example, add, you have to specify a destination and a source. The content of the source is added to the content of the destination, and the result is placed in the destination, and these flags are going to be affected. And if a carry is produced out of this addition, you place the carry inside the CF, the carry flag bit. Similarly, add with a carry, content of source added to the content of destination, added to the content of the carry flag bit. Result is placed in the destination operand. If a carry is produced, the carry is placed in CF. Increment, you specify only a destination, and this instruction will add 1 to the value inside your destination, and the result is again saved in your destination. Good. Addition. The allowed operands for add and add C. These are the allowed operand for the source when using add or add C, and these are the sorry, the allowed operand for the destination. And here are the allowed operand for increment: a 16-bit register, an 8-bit register, or a memory location. Good. Example. Addition. Move ED hexadecimal to AL. Then add 21 to AL. So 21 is to be added to ED. Okay. 1 plus D is E. 2 plus E is 0. And carry 1. Then we add with carry AL and 11. So 11 is to be added to the content of your AL and the content of your carry. So this one is going to be taken into account. This will give you 20. Midway, a carry was produced out of this addition. Then increment AL. The value now in AL is taken and a 1 is added to it. This is the result, 21. Of course, placed in the destination register AL. And if you count the number of ones in this result, you will find it even number. This is why the parity flag bit is set. Okay, and here is a schematic diagram to add 32 bits. The least significant 16 bits is placed in AX. The most significant bits are placed in BX. When you add these together, all right, a bit by bit, the result is saved in AX. If a carry is produced, it is placed in CF. Then you add with the carry. You take the carry, add it to these bits, and you add this a bit by bit till you get the result. Least significant 16 bits is here, and most significant 16 bits is here. And you have to check your CF whether it is set or not to know the exact result. Subtraction. We have 4 forms. You sub two numbers. You sub with the borrow two numbers. You decrement a number by 1 and you negate a number. Okay, similar to the subtraction, to the addition, subtract, this is the mnemonic code. You have to specify a destination and the source. You subtract the content of the source from the content of the destination. You place the result in the destination. You set the CF flag bit if a borrow was needed. Okay, always the negative sign goes with the source. Here you decrement, you subtract a 1. Negate, if you have a number and you need to change it into negative, you do this subtraction process. 0 minus the destination. Result is placed in the destination. Definitely SF is going to be 1 because you are negating a number. And if this subtraction process operation requires a borrow, your CF is going to be set as well. Okay, example. These are the operands used with the source. These are the operands used with the destination. And here are the operands used with decrement and negate. Let's see an example. Okay, move this number to CX and this number to BX. Then sub CX44. The negative sign goes with the source. This is the source. If you do this subtraction, you will get this result. And none of your flag bits is going to be affected. Then sub with a borrow. Okay, again, the negative sign goes with the source. This is the value now inside your source. Okay, then you subtract the borrow, and the borrow here is 0. The borrow, the CF flag bit is 0. You will get this result. All right. Out of this result, a borrow was needed. This is why CF is set. And the result is negative. This is why SF is set. Then decrement BX, subtract 1 from BX, you will get this. Okay, subtract 1, this will be 0. And again, the number is still negative. And the number of ones inside this result is an even number. Then you negate the value inside BX, which means you have to do this. 0 minus FD50. You will get this result. And a borrow is going to be needed. This is why your CF is set. And you count the ones, the number of ones in your result. The number of ones will be an even number. Even number because 5 had 5 as 2 ones, and if 4 ones, all in all you have 6 ones. This is why the parity flag bit is set. Okay. Multiplication. Now another instruction used with 8086, 8088 processor is a multiplication, and we can do an 8-bit multiplication or 16-bit multiplication on either signed multiplications or unsigned multiplication. So you take the sign of these numbers into account, or you just multiply the absolute values. Okay. This instruction results in a shorter program if you do write some program to do your multiplication, and a faster execution. But remember that multiplication usually results in double the width. For 8-bit multiplication, you need 16-bit register to save the result in. For 16-bit multiplications, you would need 32 bits to save your results in. Okay, so if you're multiplying two numbers, each is 8 bits, you need 16 bits. If you are multiplying 16-bit numbers, you need 32 bits to save your result in. Okay, in 8-bit multiplication, the multiplicand is always saved in AL, and you as a programmer will determine the multiplier. So multiplications, we have multiplicand placed in AL, and the number you need to multiply the content of AL with is determined by the user and is called multiplier. So we have multiplicand placed in AL, multiplier determined by the user. In a 16-bit product, the multiplication in 16-bit of course, the 16-bit result from this is placed in AX. In 16-bit multiplication, the multiplicand, the first 16-bit number, is placed in AX. And the programmer can choose the multiplier, whether to get this 16-bit from a register or from two memory locations. Okay. Where to find the result? Where the 32-bit result can be found, and you can find the most significant 16 bits of the product in DX and the least significant 16 bit in AX. So your result will be placed in AX, DX, least significant 16 bit, most significant 16 bits. Okay, in the sign multiplication, the product is true if positive, dealing only with magnitudes, and if it's negative, it will be represented by its tooth complement. So if the sign bit is 1, this number, the result is in tooth complement. So you have to reconvert it to get the true number. Good. Multiplication. This is the two forms of multiplication. You take 8-bit multiplication, multiplicand placed in AL, user determine the source to take the 8 bits from, the result is placed in or saved in AX. In a 16-bit unsigned multiplication, the multiplicand is placed in AX, the user determined the source from which we take the other 16 bits, the result is placed in AX, least significant 16 bits, and DX, most significant 16 bits. This is multiplication of sign numbers, so you take the sign into account. Again, the multiplicand is placed in AL if you're doing 8-bit multiplication, or in AX if you're doing 16-bit multiplication, and the result is placed in AX here, AX and DX. Of course, if the result is negative, your SF would be set. If positive, your SF would be 0. Good. The allowed operands used with the multiplications are these: 8-bit register, 16-bit register, or a memory 8-bit and 16-bit memory locations. Okay, example for multiplication. Okay, move 5 into BL. All right. Then 10 into CL. Okay. Then CL in AL. So You take this 10, place it in AL. So this is your multiplicand. Hexadecimally 0A. Then mul BL. So you're going to take the value inside BL multiplied by the value inside your CL, 5 decimally times 10. This is 50 decimal, which is 32 hexadecimal. So the result out of this process operation would be placed in your AX. If you check the value inside your AX, you would find 32 hexadecimally. Okay, so your AX will contain this. Good. If AL is minus 1 is represented by this value hexadecimally. Okay, the AL, the AL are all ones. Okay, good. So this is minus 128, the weight of this bit, and the rest, if you add up the weights, you will get 127. You add these together, you will get minus 1. Minus 2 is represented by this. Okay, of course, in tooth complement. So what is the result of executing mul CL? So you will take the value inside your AL multiplied by the value inside your CL regardless of the sign. This is mul. So as if you are multiplying 1, okay, multiplying this number by this number. AX will contain AL times CL. This is the value inside your AL. This is the value inside your CL. This is your result. Definitely it is wrong. Why it is wrong? Because we used the mul instruction dealing with sign numbers. We should have used the I mul. Gives you correct result. I mul will give you a correct result. I mul CL. It will take now minus 1. Okay, treat it as minus 1. Minus 2, treat it as minus 2. Your result should be now plus 2. Here you are. AX, really? Minus 1, minus 2, and then the result is 2. This is what you will get inside your AX. So you have to pay attention. If you are dealing and care about sign, you use IMUL. Otherwise, you can use mul if you're dealing only with absolute values. Okay, division. Both 8-bit and 16-bit divisions on either signed or unsigned can be performed. You use this div with unsigned numbers and idiv with signed numbers. Okay, and you have to convert the dividend into its double width. If you are dividing two numbers, the denominator is a divisor and your numerator is a dividend. All right, dividend. Okay, dividend and divisor. In doing 8-bit division, your dividend should be converted first to 16 bits. All right, because the result should be saved in 16-bit registers. Good. For example, 8-bit division, you convert your dividend into 16 bits. In 16-bit division, you convert your dividend into 32 bits. Okay. Okay. In 8-bit divisions, the dividend, the 16-bit dividend, the converted dividend from 8 to 16 should always be located in AX. And the divisor is selected by some operand. The results are two 8-bit numbers, a quotient placed in AL and a remainder placed in AH. So the 16 bits out of 8-bit divisions will be found as such. You have a quotient. When you divide a number by a number, you would have a quotient and a remainder. Quotient is placed in AL, remainder is placed in AH. We'll see this by an example. In 16-bit division, okay, the dividend is converted to 32 bits, located in most significant 16, least significant 16. And the result will be, again, quotient and remainder, quotient in AX, remainder in DX. Okay, quotient in AX, remainder in DX. And the sign of remainder and quotient should be the same. If the result is positive, your remainder should be positive and the quotient positive. If the result is negative, your quotient should be positive and your remainder should also be positive. Okay, division. Again, this is the table showing you the div and idiv. These are the mnemonic codes. When you do div, 8 bits, you would have to, as a programmer, provide a source. And the result, the quotient is placed in AL and the remainder in AH. The quotient is AX 16-bit dividend over a divisor. Okay, you as a user provide the source. Okay, you place the dividend into a 16-bit register AX, into a 16-bit register AX, and you define the other divisor 8 bits. Okay, so you provide 8-bit number, and before you're doing your division, you should place your dividend into AX, and you get the result from AL and AH. If you're doing 16-bit division, you would have to prepare your dividend into DX AX 32 bits. Then, as a user, you provide a 16-bit source, which is your divisor. Again, the quotient is placed in AX and the remainder is placed in DX. And you do the same with the idiv. You only provide 8-bit value if you're doing 8-bit division, or 16-bit value if you are doing 16-bit division. But before doing your division, you would have to prepare your dividend into AX or dividend in DX and AX. Good. The operands used either 8-bit register or memory or 16-bit register or memory. Let's see examples for division. To convert an 8-bit into 16 bits, use this instruction, convert byte to word. To convert a 16-bit into a 32 bits, you convert a word to double word. All right. These are used to prepare your dividend. before you divide on your divisor. Okay, so you have to use convert byte to word in 8-bit division and you convert whatever value inside AL to 16-bit placed in AX, and you convert a word to double word. The 16 bits placed in AX is now placed or converted into 32 bits. Okay, and this conversion is done by what we have previously mentioned, and we named it a sign extension. Sign extension. You extend the sign bit through the 8 bits in 16-bit division, or 16 bits if you're doing 16-bit division. Okay, here you are. This table is showing us the sign extension to convert a word into byte into a word, or a word into double word. So if you are converting a byte into a word, the most significant, the sign bit of AL is placed in AH. So you check the sign extension. If it's 1, you placed 8 1. If it's 0, you place 8 zeros. So this is what we mean by sign extension. Okay, so sign extension is good to prepare your dividend before division. Example. Well, you placed a number. Your dividend now is placed in AL. Before doing the division, you have to convert your byte into word. If you check A1, this is your 1 for 3 zeros. This is your A. So the sign bit is 1. So you have to place 8 ones in AH. And this is now your prepared dividend. Okay, you as a user, now if you are converting to a double word, again, AX is checked. Your sign bit now is 1. Your DX will be placed with 16 ones. This is showing to you how this conversion is made. Convert a byte to a word, or a word to a double word. Okay, example 2. This is now your AX. This is your CL. So what is the result of executing dev CL? This is already prepared, because 0 1 0 0, then 1 0 0 0. This is the value inside your AL. The sign bit is 0. We placed 8 zeros in AH. When we say dev CL, this is now your divisor. So you're taking the prepared dividend divided by your divisor, and the result is placed in your AX. If you're doing this 12 hexadecimally is what? This is 12 hexadecimally, it's 18. And this is 3 hexadecimally, which is 3 decimally, the result is 6. So if you check your result now in your AX, you would find it 0 1 1 0, and the rest are all zeros. Good. So this is your result. The quotient now in AL is 6. The remainder is in AH, which is 0. So you get the quotient and remainder. So AX now contains this. This is your quotient, and this is your remainder. Good. Let's execute this program. Minus 100 decimally is placed in AX. All right. which is minus 64 hexadecimally in its tooth complement. It will be placed as such in your AX hexadecimally. Good. Now 9 is moved to CX. Okay, so this is what's inside your CX now, hexadecimally. Good. Then you're doing 16-bit division. Again, 16-bit division, and we're given a value on AX. We have to convert it into double word. Least significant in AX as is, and most significant in DX. You check your AX. The sign bit is 1. You place 16 ones in your DX. So we have F, 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 and DX. And this is the value in AX. Then, because numbers here are negative, you do IDiv. All right. After doing so, you will get the remainder is minus 1. Okay. Minus 100 over 9 decimally. You will get minus 11 as a quotient and minus 1 as a remainder. Okay, minus 11 as a quotient, minus 1 as a remainder. These are placed in their tooth complement, which will look like this. This is the value inside your AX, and this is the value inside your DX. Okay, now another type of arithmetics, which is BCD and ASCII. We can perform arithmetic operations using the binary coded decimal digits or numbers coded in the ASCII code. All right. Application like point of sale terminals usually use the binary coded decimal arithmetic. The machine used when you buy things from department stores or supermarkets, they use the point of sale terminal. The arithmetic done by this point of sale machine is binary coded decimal operations. In some other application like the travel agencies, they use the ASCII arithmetics. But you have to prepare your numbers for the binary coded decimal arithmetics. You have to decimally adjust your number for addition. If you're doing addition, if you're adding numbers, decimally adjust for subtraction, adjust AL after multiplication, adjust AX before multiplication. Okay, and this is what this instruction does. Adjust AL after multiplication. It takes the value inside AL divided by 10 to give you the quotient placed in AH, and it takes the value in AL divided by 10, it gives you the remainder placed in AL. While adjust AX before division, what it does, it takes the value inside your AH multiplies by 10 and add AL to it. The result is placed in AL and then place 0, 0 into AH. Let's see this. Decimally adjust for addition, decimally adjust for subtraction, adjust AL before multiplication. These are used for subtracting, adding, and multiplying. While in division, you adjust your AX before this instruction. So these are done after, and this is done before. Okay, let's see this. We're adding BX. dx, and the result is placed in cx. Decimally adjust for addition. Okay, good. You move this value inside your dx. Okay, this value BCD. So this is 34, this is 12, this is 30 in a packed kind of a storage. This is placed in BX. All right, BL now is moved to AL. Now we adjust, add DL to BL. Okay, now BL contains 99, correct? While DL is 34. So we are to add 99 to 34 binary coded decimal format. Okay, after adding these two numbers, 9 plus 3 is D hexadecimally. These are BCDs, but your processor will treat them as hexadecimal digits. So, and this is C. So this is the result. But the correct result I need to get should be what? 9 plus 4 is 13. Then 10 plus 3 is 13. And carry 1. Decimally adjust after addition. It gives you 33 in AL, CF is 1. So this is adjusted to look like this. So you have to adjust your added numbers after addition to convert it to the binary coded decimal. Then move AL to CL. Okay, this is now your AL is moved to CL. This is what CL contains now. Then you do the same with DH and BH. First, BH is placed again in AL. Then you add with a carry, don't forget this, DH to AL. When you add BH, DL, CF, you will get this. Well, does not need any adjustment because 43 hexadecimal is 43 decimal. You, okay, again, adjust your decimally adjust after addition. Decimally adjust after addition, and then you will get the same here. 43. Place now the result in CH, which is 34. This is now your result. If you try to add these numbers decimally, you will get 4. Here is 3. Carry 1. Here is 3. Carry 1. Here is 3. Here is 4. So your CH now, your CX now will contain the correct value of your addition. You do the same, decimally adjust after subtraction. This is a number moved in DX, another number moved in BX, and the lower byte is subtracted first. Then don't forget to decimally adjust after subtraction. Then you place the result in CL. Then do this with the high byte, BH and AL. Subtract, don't forget subtract with the borrow. You decimally adjust your result after subtraction. Finally, you place your AL and CH. Your CX should now contain the correct results. This is adjust AL after multiplication. We're trying to multiply this binary coded decimal numbers 05 by 05. Place your multiplicand in AL. Then place your multiplier in CL. Mul CL. This is the hexadecimal results, which is equal to this decimally. Don't forget, after multiplication, adjust your AL after multiplication. So now the 25 would be placed 05 into AL, 02 into AH. This is the low byte and high byte. Again, adjust AL before division. We need to divide these. Move 0702 packed binary coded decimal into AX. Okay, 9 into BL. And you have to adjust your value of AX before division, meaning you convert 72 into its hexadecimal equivalent. Div BL, this will give you a quotient in AL, which is 08, remainder in AH, which is 00. Okay, now we're talking about the ASCII arithmetic used by travel agencies. Okay, these instructions are used with the ASCII arithmetics. AAA, numeric code, you adjust your numbers for addition. AAS, you adjust your number for ASCII, adjust for addition. ASCII, adjust for subtraction. The decimal digits from 0 to 9 are ASCII coded from 30 hexadecimal to 39 hexadecimal, and AX is usually used with as a source and destination with ASCII arithmetic. And again, here we remind you of the ASCII coded of the alphanumeric and non-alphanumeric characters. 0 is coded as 30, 9 is coded as 39. Here is an example for the ASCII arithmetics. Move 31 to AX. This is a decimal digit of 1. Add 39 to AL. 39 is the decimal digit 9. The result, if you take this, your processor will result in 1 plus 9 is 10, which is A. 3 plus 3, this is your result. But we know that the decimal addition should result in a 10. So we have to adjust, ASCII adjust for addition. This will clear your AH if the sum is less than 10, and adds 1 hexadecimal to AH if the sum is greater than 10, and the AAA, ASCII adjust for addition, would result in 01H in AH, 00 in AL. So AX would contain this. So the result is, this is the least significant decimal digit. This is the most significant decimal digits. After doing so, you would have to add 30 to the result. So your result would be 0 is added to a 30, 1 is added to a 30, 31. So this is the ASCII code of your result, which is equivalent to 10 decimal.